right, in this video, I'm going to do a video that looks at the next part of this. So notice on questions 18 and 20, you have a rational function. So the degree on top is bigger than the degree on the bottom on both of these. And so what you wind up doing on this sometimes is to try to factor to see if you could simplify, but this doesn't factor. And then if that doesn't happen, what I'm going to wind up doing is trying to rewrite this expression so I can use the power rule whenever possible. But what winds up happening is the last term winds up being something that involves the natural log. Okay. All right. So the idea is it's almost like you have an improper fraction to start with. You could use division to rewrite it in an equivalent form. For instance, 2 would go into 7 3 times, and there'd be a remainder of 1. So that equals 3.5. And so what we have right in the beginning on number 18 is an improper fraction. And what I'd like to do is rewrite it so it's a mixed number, basically. And so we can use long division to do that. Synthetic also at times, but long division will work even when synthetic doesn't. So I'm just going to use that notion. So long division is basically just like the long division algorithm you learned way back. So x would go into 2x squared, 2x times. So now I'm going to multiply 2x times x minus 2. So I'm going to multiply back and get 2x squared minus 4x. You usually do this in your pre-calculus class. Right? And now at this point of the algorithm, I need to subtract is what I meant to say. And I'm subtracting that whole thing. So I like to distribute the negative throughout, and then I can add straight down so I don't mess up on my positives and negatives. So 2x squared minus 2x squared cancels, and then positive 7. And oops, that should be a positive 4 right there. You change the signs so that you can add straight down. Then a positive 7 and a positive 4 would be a positive 11x. This is where people mess up when they do division a lot of times. All right, then we're going to bring down the minus 3, and we're going to need to divide again. So x goes into 11x 11 times. When I multiply back, I get 11x minus 22. Getting ready to subtract. So I'm going to run through and change the signs and then add straight down. 11x minus 11x cancels. Negative 3 plus 22 is positive 19. Okay, so that scratch work means that this original problem could be rewritten as the mixed number 2x plus 11 plus the remainder over your divisor. So notice the 2 that I divided by when I did the numerical example wound up being the denominator of the fraction. All right, so what I had originally is really equivalent to me trying to integrate this expression. And so once I did that, now I can do term by term integration, and I can use the power rule on the first 2. This would just be x squared. This one right here would just be 11x. And then notice there, I've got that 19 over x minus 2, that x minus 2 to the first power. So I can't use a power rule type approach. I'm going to have to go to natural log. And that constant 19, I'm just going to bring down, and then I'll have the natural log of x minus 2, and then plus c. Okay. All right, so that's going to be my answer on that one, and I'm done. All right, so let's try one more. On 20, I put an example where I was going to have to put in a placeholder somewhere. See, I have the x to the third, but then I don't have the squared term. So I'm going to put in 0x squared minus 6x minus 20. So when I do that, x goes into x to the third, x squared times. I multiply back, get x to the third plus 5x squared. Getting ready to subtract. So I'm going to change the signs. And then I wind up with a negative 5x squared right there. Okay. Then we'll bring down the negative 6x and then divide again. So x goes into negative 5x squared, negative 5x times. You multiply back, get negative 5x squared minus 25x. Now you're going to change the signs because you're subtracting, and a minus b is the same as a plus the opposite of b. Subtracting is the same as adding the opposite. So that's why we can do that. So negative 5x squared, positive 5x squared cancels. Negative 6 plus 25 turns out to be 19x. Okay, that's where all the mistakes are typically made, is in that portion, the subtraction portion. Then I'm going to bring down the minus 20. I got to divide one last time. I have to divide more here, more rounds here, because the degree on top was 3, the degree on the bottom was 1. So I had to go 3 rounds when I did my division. Okay. All right, and then when I do that, I get a 19x plus 50 plus 45, 95. Okay. And I got to subtract. So I'm going to change the signs, because when you're working with integers, it's easier to be thinking about adding stuff. So 19 plus a negative 19 would be 0. Here I'd have a negative 115. All right. Let's see. I'm going to need room to write this. I'm going to rewrite this expression right here as a mixed number, and it would wind up being x squared minus 5x plus 19. And I'm going to use the minus right there and put the 115 over x plus 5, like that. Okay. All right, and then let me do the term by term part. Let's get a little room. Let's go to here. Then wouldn't that be x to the third, but I'd need a 1/3 out in front to cancel out the effect of bringing the exponent down. And then x to the second, I already had a 5, and I'd need to have a 1/2 along with it to cancel out the effect of bringing the 2 down. Then the integral of 19 would be 19x. And then here we are again. Here at the end, I've got a situation that x plus 5 in the denominator, it's just to the first power. So here I'm going to have minus the natural log of the absolute value. Oops, I missed the constant. Let me put the constant in. Minus the constant 115 times the natural log of x plus 5. I knew I didn't have enough room. And then I want the plus c in there. I'm going to erase this out of the way so you see what I'm trying to put in there. Natural log of x plus 5, and then I need the plus c on that as well. And that would be it. All right, now, this part that I'm showing you right here, this idea of dividing when you have a degree of the numerator being more than the degree of the denominator or equal to, being able to change it into a mixed number like that allows you to do the term by term integration. And then oftentimes, not all the time, but oftentimes, this last term would be something where you might need to use natural log, or there's times when you do that kind of division and what you wind up with is something where you need to use like an arc tangent. It's an arc tangent situation. So it fits what we see in section 5.8. So you do more of that when you get to calculus 2 if you're taking that. All right, in this video, I also want to introduce how sometimes when you're dealing with trig functions, natural log is going to come into play. And I want you to see why that is. I don't like personally memorizing things. I like to be able to just figure them out, especially tangent. I don't need to know this rule because it's just as easy to do it by figuring it out. And I'll show you what I mean. All right, so up until now, the only things that you can integrate, the only trig function related stuff you can integrate are things that wind up, if you're trying to integrate something like cosine x, because it was the outcome of a derivative problem. Like cosine x you would get if you did the derivative of sine. So you can integrate this because you know it came from sine. You know that derivative rule. So any trig related thing that was the result of one of the derivative rules is what you've been able to handle so far. So for instance, the integral of secant squared x dx, I recognize secant squared as what you get when you do the derivative of tangent. So the integral of secant squared x dx would be tangent x. All right, and there's others, like you would be able to do cosecant x, like you could do the integral of cosecant x cotangent x, because you recognize that as having come from cosecant. It's just that when you do the derivative of cosecant, you would get have to have a negative on that. So I'm going to put a negative there in order to have that negative disappear once I do the derivative of cosecant. Okay. All right, so the only kind of trig stuff you can do so far are these kind where what you're trying to integrate is actually coming from something in chapter 3, what the answers in chapter 3 wound up looking like. Okay? So then the issue is, well, how do I integrate then just something like tangent by itself? So that's what I want to show you in this video. And then in the third video, we'll go on and work a couple problems related to that. There's not very many that you really need to know how to do. All right, so let me erase this and kind of clean it up, and let me show you where these first two rules come from on the left, how you can derive them. The first one is coming from the fact that the definition for tangent is really sine over cosine. Okay. So you see, I've got the situation where I have a 1 over cosine with a sine u du. I could think sine, I need the u on that, sine u du to the right. I could think of it like that to see better what's really going on. All right. And then when I do the derivative, something like this, okay, the 1 over something, I know that is going to equal the natural log and the reason why I need to have a negative in front of it, let me show you that. Let me do the u substitution that I was not going to do. So I'm thinking about how this is 1 over something and how that sine u right there came from the derivative of cosine. But let me show you that better. I can't use a u because they already have u's. So let me use a v. So v, let's let some variable stand for cosine u. Then dv would equal negative sine u du. Okay. And then I see the sine u du, but I don't see the negative. So I'm going to divide both sides by a -1 and get that sine u du. All right, so then I'm realizing that this problem is really the same as integrating 1 over u, 1 over v, 1 over v dv. Okay. Not strictly dv, negative dv, right? Times negative dv. All right, so I just need to integrate a -1 over v dv. So when I do a 1 over, that's going to be natural log, okay, of the v. The negative is a constant that I can bring down, and then I need to do the plus c. Make a little more room there. So natural log of v, I'd have a negative out in front and then a plus c, and v is the cosine of u. So that's where that came from. And in fact, when you do a tangent problem, a lot of times you just do it that way rather than having memorized that formula. All right, now these others, the cotangent one, you could figure out yourself as well. Or once you know tangent, you can see the relationship. See, instead of cosine over here, it's the opposite one, it's sine. And tangent had the negative, so cotangent has the opposite. It's positive there. All right, but you might want to just know those rules. I would say figure out tangent and then know the relationship between the tangent one and the cotangent one. All right, let me show you the trick, the idea behind developing the rule for the integral of secant u. The thing is, with secant, yes, we could do it, but in order to see where this one came from, you actually have to understand this trick. And if you understand, this idea, and if you understood this idea, then you basically have the rule memorized anyway, because it really comes from what I'm trying to make happen here. That's kind of the idea behind it. Here's the proof that this is true. Okay, what I can do is take my secant u that I had to start with. Where are you? Sorry. I can take that secant u plus tangent u. Notice that secant u plus tangent u that I had in there, and I'm going to try to get that into the mix somehow. So what I'm going to wind up doing is multiplying the top of the original function and the bottom. So I'm talking about this right here. And if I touch my touch screen, it moves. And the bottom is like an understood 1, so I'm going to multiply the denominator by that as well to make it okay to have done that. All right, let me get myself a little room right here. See if I can get go. All right, so that's the idea that you'd have to know in order to prove that this rule works. And so really, if you know that trick in order to prove that this rule works, then you must already know the rule. So you just need to know this one. But I'm just showing you where it came from. So here's the idea. Then that numerator is really secant squared u plus secant u tangent u, and you should recognize each of those as being the derivative. Secant squared u is the derivative of tangent, and secant u tangent u is the derivative of secant. Okay? So here's going to be the idea. So I'm going to let I'm going to do it over here. So I'm going to choose a variable. I can't use u because there's already u's, so I'm going to use a v. I'm going to let v equal the denominator, secant u plus tangent u. Then the derivative, dv, would equal the derivative of secant, would wind up being secant u tangent u. The derivative of tangent would be secant squared u. Okay, and I would have to do the derivative of the variable, so the derivative of u. Okay. Now, when I look at the problem and I analyze it, I see, oh, this works out great because here I have 1 over secant u plus tangent u. And then right here is the secant squared u plus secant u tangent u times du. See right there. So I'll be replacing the secant u plus tangent u is really what v was. And then now all of that in the box is actually dv. And so this turns out to be the natural log of the absolute value of v, which is secant u plus tangent u, and then throw the plus c on it, and you have the rule. So that's just the proof of that rule. All right, so if you really were faced with trying to do the derivative of tangent, okay, and you're not a big memorizer, you could handle it. Really, I didn't even have to teach that to you. Let's see if I can get that. All right, I didn't really have to teach that to you because you would have probably tried to do what I showed you when I derived it. So really the way I do it is basically like this. and I think of it as 1 over cosine x with sine x dx over here. And I think about, oh, this is a natural log situation. Okay, but when I do the derivative of the inside, I would get negative sine x. So I need to adjust and put a negative on this to cancel out the negative I would get when I do the derivative of the inside function. And then there's my answer. Okay. All right, so the rest of this is done in a separate video. Oh, let me comment a little more. So back to the rules then. You need to know these or figure them out. So you really can survive just by working these out using the normal U substitution, except the ones on the bottom, you would have to understand that trick of multiplying the top and bottom by that secant U plus tangent U in that case. And I don't think you would think to do that unless you already knew what the rule was. Okay, so I'm going to stop it now and